So let me see what you guys covered last week. So as mentioned, in order to learn the machine learnings, I believe there's the mathematical backgrounds that we need to learn. So the first topic I believe is linear algebra. So I guess you cover the linear equations and how do you use the Pythons to compute the linear equations. And when you have a system of linear equations, we can transform it in the matrix form. And there are two ways that you're supposed to look at the matrix. The first one is columns, the collection of columns. The second way is that the collection of rows. So those two that I mentioned it. And of course, we have some operations in the linear space. So one would be the vector product of vector and vectors between the vectors, and it will be the inner product. And we do matrix and vector multiplications that you guys already know. And there's some properties in the matrix. One is the symmetry, and we can define like distance or strength in the linear space. And I mentioned norms, like two norms and one norms. Those two, the concept of distance, you're gonna see a lot in the following lectures. And how do you compute it? Don't worry about it, because we can use Pythons to compute it. And once we define the distance, the concept of distance in the linear space, we can come up with the definition or concept of orthogonalities. What's the right angles between the component in the linear space or two vectors in the linear space. And from the orthogonalities, we can define the angle between two vectors and so we're gonna use these concepts, the angles between two vectors for classification problems. So we can divide it to different space into the subspace using the angles between two vectors. So we will come back when you discuss classifications. And the second topic is, again, let me see. It was the matrix and linear transformations. So the message that I want to point out in here is that we talk about different linear transformations a lot, and as always, there is an associated matrix. So from matrix, it's important to come up with some corresponding linear transformations, and vice versa. Starting from the linear transformations will be the associated matrix. There's those two. I hope that you are able to look different perspectives whenever you look at either matrix or linear transformation. So whenever you have questions, you can turn on the unmute microphone, or you can always chat to communicate with me. And I have two computers, so I have another computers that I'm looking at the screen, so I can notice whenever you give me the message or chat. So okay, let me continue on. So some of the example of linear transformation that I address here is rotations and stretch and compress and projections. And at least for me, it's not intuitive that rotations and the projection is one of the linear transformations. It's not intuitive. So think about it. And here from the definition of linear the rotations, how can we come up with corresponding matrix? These are, so here, as you can see, these are the corresponding matrix that represent the rotation transformations and the projections as well. And here is the multiple transformations. Whenever we have a sequence of the linear transformations, it will be represented by multiplication of matrix, right? So that's the, and here I gave you some of the definition of linear transformations, and always there's two conditions that you have to check: superpositions and homogeneities. And these are fundamental things that you have to keep that in your mind. To whenever we talk about the linear transformations, there's two conditions that you have to check. And in another topic was that is in the linear space, or let's say it's matrix, is eigenvalues and eigenvectors. The key is really important. It's really important to understand, for you guys to understand what's the physical meaning of eigenvalues and what's the physical meaning of eigenvectors. Right? I know already most of you guys know how to compute. Given matrix, you can compute eigenvalues, eigenvectors, but that's not enough. Always, I hope that you are able to see or get some insight or some ideas from the eigenvalues and eigenvectors. Whenever you have either matrix or linear transformation, it doesn't matter. So here, the way that I explained on how to find the eigenvectors and eigenvalues is that given a matrix, think about the corresponding linear transformations and think about the definition of linear transformations, either rotations or projections. From that definitions, how do you come up with eigenvectors that does not change, right? From the the given linear transformations. Right? So that's and of course we can do eigenanalysis in Python. And here is some of the example that I provided is eigenanalysis of projections, which is linear transformation as well. And the mirror too. And rotation is very interesting stuff. I hope that you take some time to think about what's the eigenvectors and eigenvalues in the rotation linear transformation. That's not so here it's very at least for me it's really interesting way for whenever you think about the rotation matrix or rotation linear transformations, think about the corresponding eigenvectors. Right? In the real space does not exist. But if you expand it into complex plane or complex numbers, right, we have another z vectors, which is the axis of rotations. That's kind of thing that I hope that you guys can catch. Now, I think that's where we stopped last time, and I'm going to continue on the last topic in the linear algebra, which is system of linear equations. And let me, oops. So I'm going to start from here. So let's see, so you guys learn the linear equations. I mean, that's from, how do I say, from middle school or high schools. And here what I want to discuss is system of linear equations. Whenever you have multiple or more than one or two linear equations, there's some interesting things happening. So there are 3 different categories. For me, it's the way that I split it or divide it in the system of linear equations. The first thing is where determined or where determined. linear systems, and second is underdetermined. The last one is overdetermined. I'm going to explain what it is one by one in the following slide. So let's think about where determined linear system first. So it's where determined. Suppose you have, so just let's think about this. I think you already did that. And so we have one linear equation and another linear equation. So we have two linear equations, and we know that x of 1, x of 2, we have two unknowns. So before you actually compute the unknowns, so looking at the system of linear equations, always there's two, in this case, there are two linear equations. That means there are two constraints and we have two unknowns. So let's see, we have two unknowns. And maybe you'll say two equations or two constraints. So let's think about the first equation first. We have two, say x of 1 and x of 2. We have two unknowns. That means two-dimensional space, x of 1, x of 2 can have any values unless we have these linear equations. So we can have any values, but there's some constraint, x of 1, x of 2, those two values have to satisfy this constraint. Has to satisfy it. So that means, let me see, maybe that's the guy you, so let me, so I don't know, let me, maybe like that. I mean, so these points on top of a straight line will satisfy these. And we can repeat the same thing here. There's another, right? So in geometric point of view, that's really important. And just forget about these, how to find the solutions. So two unknowns in two-dimensional space, you have two equations. I mean, I just draw this. And suppose these satisfy the first, and these, the points, satisfy the second equations. But what we want to find out is that there's something satisfy these two equations at the same time. Then there is only single point. That's gonna be the solution for that. Okay. So there's in general, we can find out for where determined linear systems, we can find out the solution. But if you think about it from the geometric point of view, say there's only single case if these two lines are parallel, there's no solution exists. Otherwise, there's always, we can find out the single solution for that. And this is, now let's move on to another perspective, looking at the system of linear equations in the matrix form. For me, it's how do I say, in the matrix is like we have some numbers inside it. So whenever you have how do I say, system of linear equations or multiple data points, always you can put them together, try to build up or construct in the matrix form, because it's a really intuitive or easy to handle the many data sets. So let's do the same things. So given these, and I can transform it in the matrix form like that. And here it's a matrix. In this case, it happened to be 2 by 2 matrix. We have X unknowns, and we have, say, bias or constant. And in this case, the solution is that, I mean, you already know that if the inverse of a matrix exists, we can compute it, and we can do X is A transpose A inverse B. So we can find out solutions. And let me ask, when the inverse of a matrix does not exist, that means if we cannot find the inverse, then there's no the exact solutions for that. So from the matrix perspective and the geometric here, if we have two parallels, that means in a matrix, I mean these, say, let me like that. If we have the same slope, then these two linear, the lines are parallel. So in that case, does not exist, and the solution does not exist, and we know that the inverse of a matrix also does not exist. Right. So these two are related. So I hope that you guys can see both of them at the same time. So let's move on to the next category, is underdetermined linear systems. In here is where determined is, what I mean by that is number of constraints and number of unknowns are the same. So whenever you build up the matrix form from the well-determined linear systems, you're going to see matrix which is in square, right? The X and Y are the same. The dimension of these two, I mean, in the square matrix. But here, under determined linear systems, as you can see, this one is one of the examples that I provide here. And as you can see here, number of unknowns are larger or more than number of constraints or number of equations. So in that case, we know that all the solution that satisfy this is many solutions. In the geometric point of view, there are many data points that satisfy these. So keep that in mind. Underdetermined, there are many solutions because the number of unknowns are larger than number of constraints or number of equations. In the matrix form, same, repeated. I mean, in the matrix form, A, X is equal to B are the same, but the dimension or shape of A matrix are different. In that case, as you can see here, just remember the shape or the dimension of the shape of A matrix is flat. So if you're looking at this, the A matrix far away, you can say the shape of A is flat instead of square. So whenever you have flat matrix, that means they're underdetermined, and means that there are many solutions instead of having one exact solution. And let's move on to last categories with overdetermined. That's the totally opposite way of underdetermined linear systems. Here, example of system of linear equation here. Again, number of unknowns are 2, and number of equation or number of constraints are 3. Right? In geometric point of view, we have, say, in 2-dimensional space, we have in that case, if three, how do I say, 3 lines, right? So say this is the first and second and third, and this one, that's the intersection point from the first and second, probably solution of these two. And this one is the solution of these two equations. And this one is probably solution of these two. But as you can see here, in general, there's no solution that satisfies 3 equations at the same time, 3 constraints at the same time. So in general, there's no solution. But in some, maybe like, right, in that case, you might have the solutions, but that's not the general case. So for underdetermined case in linear systems, in general, there's no solution for that. Let's move on to, and let's repeat the same things and transform it in the matrix form. Right? It's in the matrix form. It's the same. A times x is equal to b, but the only difference is that A, the shape of matrix A, is skinny. Again, looking at matrix A far away from, then you will see the skinny matrix of A. Then you have to think, okay, that's the linear system is overdetermined. So in general, there is no solution exists. Right? And let me see that those are the summary of linear systems. Put everything in the matrix form are the same, but the shape of the matrix of A might be different. So in squared and fat and skinny. All right. And let me ask at this point, and in machine learnings, I didn't explain what the machine learning is, but say there's some given data points, you want to get some hidden patterns, or you want to generalize the patterns out of the data points to build up the generalized models out of it. And what do you think in machine learning? If somehow say you build up the matrix of A, you think that's the shape of matrix is just squared or skinny or fat? What do you think? What do you think? You can put your thought on the chat. No? Nobody?
Sorry, can you repeat your question, please?
Say that again.
Can you repeat your question, please?
Okay, so this, I mean, here I summarize the linear systems and say everything transform it in this form. And the only difference is that whether the system is well determined or underdetermined or overdetermined, the shape of A sometimes is squared or fat or skinny. In later on, when you do the machine learning, say suppose there's some given data points, you're going to build up the linear systems. In that case, what do you think the shape of A? It will be the squared or fat or skinny?
Probably square, I think.
Probably square, okay. And other thought? So we will revisit it, but says in regression problems. Let me see. So yeah, it's someone said it's in the regression problems. You will see the skinny matrix. I mean, I will explain it again when you discuss the regression problems. But so keep that in mind. In machine learning is all about the skinny matrix of A. So let's go back to this one. Now I explained it, there's no exact solution exist to satisfy these three different the constraint. But say we can stop here, say there's no solutions, but let's say we do the engineering problem, say what's the second best? What will be the best approximations? We know that there's no solutions, but approximations will be the second best. So probably I will say someone like between these triangles. So we know that this one is not the exact solutions, but probably one of the good candidates to approximate the solution. So again, let me repeat it. The machine learning is all about the approximations. So machine learning is all about the approximations. Because we have a bunch of data points we will get, or we will observe, or we will measure the bunch of data sets. And we want to approximate that represent the general pattern of the data points. So it's all about the approximation problems. In a geometric point of view, it's all about how to find these approximated data points in overdetermined linear systems problem. Okay, right now probably some of you don't know what I'm talking about, but when you discuss the regressions or classification problems, everything's gonna get clear. So don't worry about it if you don't understand what I'm saying at this moment. So let's find out some of the solutions in the either overdetermined and underdetermined systems. So first one is underdetermined linear system here, and here is a fat matrix of A. And we know that there are many solutions. There are many solutions. Then, for underdetermined linear systems, we know that there are many solutions, but say I want to pick one of them. I want to pick one of them. There are many ways that we can pick. I can randomly pick, right, one out of many solutions. Or we can put some constraint on it. Say, one of them is that the example is that find the solution is that minimize distance or strength or norm of vector of x, and that squared as well. Now then it turns out now it's optimization problems. I mean, this is first time that I mentioned optimizations. Probably later on we have another the topics that we want to discuss optimization. But here, I mean, you know that optimization. So here I want to minimize. This one is, I mean, subject to this constraint. Right? We know this is constraint. We know that many solutions at this moment. Among those many solutions, I want to pick one of them that minimize the distance or strength of that x, the vector x. I want to explain the same problems that I mentioned in geometric interpretations. This one is, we know that in, say, in 2D space, these are all the solutions. But what's the definition of this? This one is that Euclidean distance from the origin, right? So I want to minimize the Euclidean distance because this is the origin. Probably say this one is one of the candidates, and these, suppose that's the, and the squared. Then let me ask, what's the minimum distance? What's the point that minimum distance from the origin? I guess this guy will be the optimal solutions, right? I mean, here again, it's optimization problem. There are many solutions, but optimize what the solution is only one. What do you mean by the optimal definition? That's the definition that I define it. I want to minimize the distance in the sense of Euclidean distance. You can put, say, in one norm subject to, you can do this as well. It's really up to the way you define your objective functions or things like that. Then the optimal solution might be different, but it's okay. So this one is geometric interpretations, and I guess there's no, I mean, you guys can understand. And select one solution among many solutions. And this one we often see in the control problems. And actually this is how you compute it, but don't worry about it, right? How do you compute this? Don't worry about it. We call it least norm solutions. And on the other side, say like here, if the matrix of A is fat, it's overdetermined. And let me see. Let's think about this one. In general, there's the no solution exists, and I want to find approximated solutions. Say I want to find out X that minimize the errors. Let me see. Let's see. A X. I want to solve this one, but if in general, if A is a skinny matrix, we cannot find out solutions. And what's the second best that we can do? I want to approximate it. I want A times X and B as close as possible. I want to find out X. So AX minus B, I want to minimize by changing the value of X or factor X. Again, that's another, it turns out to be another optimization problem. So we call it least square. So let's say in most cases, in a sense of two norm, just squared it. So it's a least square solutions. And if you look at how do you find to compute the least square solutions in the Google, you will see that the many solutions. And here, the way that I want to show you here, A matrix, let's see, these two column vectors, right? And in the previous lectures, this one is linear combination of two column vectors in A with a different coefficient or weight of say A. So I will say A1 vector, A of 1 is A2 vectors. Like that. And we have x of 1, x of 2. This one is a linear combination of the column vectors in an A matrix. That's what with these rescaling factors or coefficient, weights, whatever. And again, this is vector. Having different values of x of 1, x of 2, we will have different vectors, but based on these two A of 1, A of 2 vectors. Suppose this is A of 1 and A of 2. And if you have 1 and 1, probably this will be the vectors. And if you have 0 of 1, no, we say minus of, then probably this is another vectors that we can represent it, having different values of x of 1 and x of 2. I want to change the x of 1, x of 2 values to 2. What's the purpose of that? To make as close as possible to B matrix and B vector. That's the minimization problems. So let's see, these are the solutions. And again, don't worry about how it looks complicated, but I will go through one by one. And geometric interpretations. Again, this is A matrix, A vectors. Yes, A is A2. So this is A matrix. And I think this is typo 2, 2, 3, 2. So we have two column vectors and AX having different values of X. I can span it. So the possible way of these, the plane. Okay. I hope you know what I'm talking about. So these two vectors, X is unknown. We can change, we can have any X, any values. Then there will be another vectors, but the vectors already should be on that, on top of that plane. I mean, not B, it's just like say Y. Suppose we have B matrix on top of this plane, then we can find exact solution of Y or exact solution of X. But in general case, B matrix that doesn't have to be on that plane. It will be out of planes like that. Then having different values of X, there's no way that we can reach that, reach to the vector of B. There's no way that we can do it. That means there's no solutions. There's no exact solution of X. But I said that what's the second best? Will be the best, second best, what's the best approximations? I guess I want to minimize the discrepancy. We know that this is the B that I want to reach at, but somehow I have to leave on this plane. Then the second best, again here, There will be the solutions. So make projections. Suppose B star. For B star, we can find X star. Okay, so it would be good to find the X that to make sense of B, but in general, B will be out of plane. So make projections on top of, we call it B star. For B star, we can find out A star. So that would be the optimal solutions. Here, this is that's the same thing in say in the different the linear space. So how do you find the solution of this? Let's say this is the given solutions. I want to derive that with you guys. Before that, let's think about the simpler case. So let me vector projections onto Y. So we have X. I want to find out this because say this is given. I want to make projections on it. Because why we need to do this? Because I have to make projections on V vectors onto this plane. This is a simpler version of that. Let me see. So the W vectors that this is what we want to compute it. This one is same is in the same direction of Y, but Y does not normalize it. So I will say the scaling is omega. Okay, and let me see. Say this is the unit vectors. The length of length is 1, but the same as the direction is same as Y. And let's compute the omega. Omega is here. The length of this guy is omega, and we can apply omega is the length of X cosine theta, and the cosine we know that X the angle is Y inner product. We do that's the we use the definition of inner product, and we can cancel it out. So that's the omegas, and I'm going to plug in that here, and omega is like that. Okay, and let me see. That's inner product. This one and this one is inner product between X and Y, and this one is inner product of Y itself. So that's the how do you compute it? And let's move on. Let me see another way of computing the omegas and W. This is something that I like. And I know, let me see why. We don't know omegas, but we want to find out the omegas. And say, let me see, X minus omega is this factor. And because we made a projection on top of Y's, we know that these and Y are orthogonal. We want to find out omegas that satisfy this condition. And let me go back, and we can think about inner product zeros, right? And Y transpose X, and omegas, W's. We computed W's. Where is it? This one is omega y divided by y length transpose x. Omega is just scalars. And we know that zeros. Then we can compute omegas. Omega is this omegas we can compute. Divide by, let's see, y transpose x and y transpose y. And that's the omegas. Again, W is omega and y hat. So we know that this one is x and y inner product. And this one is y product itself. And let me see. This one is y divided by, so we do y because we cancel this out. So it's the same as the previous one, but here is it's another way of computing to find out the omegas or projections. So what we did is that given any vector of x, we can find out w vectors, which is projections onto any y vectors. Now let's go back to the original problems that we have. I want to do orthogonal projections on the subspace. Here I mentioned these are the subspaces space that I'm interested in. All right. So let me again. I'm going to use the second method that I just mentioned here. And these vectors are orthogonal of the vectors are orthogonal on orthogonal with the plane. So because is a x of star minus b. This one is orthogonal of a1 and at the same time this. Then what we can do, a1 transpose we just right orthogonal constraints in the matrix form. Here, what we can combine it this one A matrix. Now A transpose A x time the star A transpose B equal to zeros and transpose B A transpose A inverse A transpose B. That's how we compute this guy, right? I use a geometric the interpretations to because the optimal solution has to be orthogonal. So I use that properties to compute x star, which is the best approximations in Euclidean sense. So we're going to use this one a lot, especially when you talk about the linear regression problem. So for that one, I want you guys to memorize it. A transpose A inverse A transpose B. You have to memorize it because we're going to use that a lot. All right. So that's all the materials that for linear regressions. I mean the linear algebra.